So now we're going to move from power cycles to refrigeration cycles. In nature, heat flows from hot to cold, so we need a specialized device to cool things down below ambient temperature. Refrigeration is this process of transferring heat from a lower temperature to a higher one, with the goal of even further cooling this cold temperature reservoir. The exact opposite scenario to this, that is, pulling heat from a cold reservoir to heat up an already hot reservoir, is called a heat pump. These are actually the exact same device, but just have a different purpose. So in this analysis of refrigeration cycles, we'll also talk a bit about heat pumps. Refrigeration cycles are very similar to the power cycles we have seen over the past week or two, but just run in reverse. The working fluid in refrigeration cycles is called the refrigerant, and there are many options for what to use for this. It can be a gas, in other words, remain gaseous for the entire cycle, or vapor, going between gas and liquid throughout the cycle, as well as some other options like cascading and absorption refrigeration. Instead of efficiency, the performance of refrigerators and heat pumps is given by the coefficient of performance, or COP. For refrigerators, this is the cooling energy out divided by the work in, or QL over W net in. For heat pumps, we are looking at the heat added, so the COP is equal to QH over W net in. Unlike the efficiency, the coefficients of performance can be greater than 1, and in fact, the COP for heat pumps will always be greater than or equal to 1. But heat pump COP is equal to 1, then it is equivalent to a 100% efficient resistance heater. Cooling capacity is sometimes given in something called tons. This is equivalent to the amount of heat needed to freeze 1 ton of liquid water in 24 hours, all at 0 degrees Celsius. This is equivalent to 211 kilojoules per minute, or 200 BTUs per minute. So to begin the analysis, we need to decide which idealized cycle to use. Since refrigeration is like power cycles in reverse, we can start with the reverse Carnot cycle. This looks exactly the same as the forward Carnot cycle, but everything works backwards. The 4 internally reversible processes in this reverse case are, from 1 to 2, we have isothermal heat addition from a low temperature source. Low temperature refrigerant enters the evaporator and comes out with a higher temperature. From 2 to 3, we have isentropic compression, which increases both the temperature and pressure of the refrigerant using a compressor. From 3 to 4, there's isothermal heat rejection to a high temperature reservoir. In this process, the refrigerant changes from a saturated vapor into a saturated liquid in the condenser. And finally, from 4 to 1, we have an isentropic expansion through a turbine, lowering the temperature of the fluid and returning it to its original state. Over here, you can see a graphical representation of the cycle and all of the processes, as well as the TS diagram for this reverse Carnot cycle. For this reverse Carnot cycle, the coefficients of performance are given by COPR equals TL over TH minus TL for the refrigerators. And remember that the temperatures must be absolute. While for heat pumps, it is COPH equals TH over TH minus TL. As usual, the reverse Carnot cycle is the most efficient system for either refrigerators or heat pumps. However, it is not a great cycle for refrigeration systems, or heat pumps for that matter. For similar reasons to what we saw in the previous video, for vapor power cycles, this would require a compressor that can handle both liquids and gases, and would have a significant liquid content through the turbine, which is also not good. The cycle used in the analysis of refrigeration systems is called the ideal vapor compression refrigeration cycle. No fancy name like Otto or Brayton for this one. This modifies the reverse Carnot cycle by entirely vaporizing the refrigerant before the compressor and replacing the turbine with a throttling device, which does not depend on the phase of the fluid. The ideal vapor compression refrigeration cycle is composed of the following 4 processes. 1 to 2 is an isentropic compression using a compressor. This is where work comes into the system. The refrigerant begins as a saturated vapor, and as temperature increases as it is compressed. 2 to 3 is a constant pressure heat rejection using a condenser. Superheated vapor comes into the condenser and leaves as a saturated liquid, but still at a high temperature. 3 to 4 is throttling and an expansion valve. Throttling is the thermodynamic process of changing a high-pressure fluid into a low-pressure fluid. Saturated liquid enters and leaves the throttling device, but leaves with a much lower temperature and pressure upon exit as a saturated mixture. And finally, from 4 to 1, we have a constant pressure heat input into the fluid from an evaporator. The refrigerant enters the evaporator as a low-quality saturated mixture and leaves as a saturated vapor. The whole process can be seen here pictorially and here on the corresponding TS diagram down here. The best example of a refrigeration device is your household refrigerator. Tubes in the freezer compartment act as the evaporator, while the coils behind the fridge are the condenser. There's a compressor installed somewhere in there, and the throttling device is usually a capillary tube. As the refrigerant moves through the system, electrical energy is converted to work put into the system in the compressor. Then heat at a high temperature is dumped into the kitchen air from the condenser coils, while low temperature heat is dumped from the evaporator coils into the freezer compartment, cooling it down. The area under the TS diagram represents heat in or out, and the area enclosed is the work required to be put in. So the area under 4.1 is the heat absorbed by the refrigerant in the evaporator. The area under 2.3 is the heat rejected in the condenser, and the difference is the work required to be put in. As a general rule, the COP of a refrigerator will improve by 2 to 4% for each degree Celsius of temperature difference between TH and TL. Remember that for a Carnot cycle, the larger the temperature difference, the bigger the efficiency. In addition to the TS diagram, a pH diagram is useful for the analysis of refrigeration cycles. In this figure, the heat transferred is proportional to the length of the lines between 2.3 and 4.1. This can give an easy and quick visual representation of the ratio of the heat in to the heat out. For this particular example, it looks like the QH line is about 40% longer than the QL line. So here's the QH line, and again, length of it longer than this QL line. So there is about 40% more heat transferred from the hot reservoir than the cold reservoir in this case. Unlike all the other cycles we have analyzed in the past few videos, this one does not have 4 internally reversible processes. This ideal vapor compression refrigeration cycle has only 3. This is because the throttling process is actually irreversible. This changes the TS diagram we saw a couple of minutes ago. What happens here is that the process 3 to 4 ends at number 4 here. In all the previous ideal cycles, including the reverse Carnot cycle, this expansion process was isentropic, so we had a vertical line, such as this one, going from 3 to 4, or 4 prime here. Because of this difference, we get a lower refrigeration capacity using this cycle, which is not too surprising since there's irreversibility involved. Now for the analysis. All 4 processes happen under steady flow conditions, and there's no significant change in kinetic or potential energies. The first law of thermodynamics for this entire cycle then becomes Q in minus Q out plus W in minus W out equals HE minus HI, which should be 0 because it's a closed cyclic process. And with Q in equals QH equals H2 minus H3 in the condenser, Q out equals QL equals H1 minus H4 in the evaporator, and W net in equals H2 minus H1 in the compressor. So COPR is H1 minus H4 over H2 minus H1, and COPH is H2 minus H3 over H2 minus H1. These are generally calculated in practice by knowing the temperature and or pressure of the refrigerant and finding the values of the enthalpies in property tables. Specifically for the ideal case, H1 is the enthalpy of the fluid in the gas phase at the pressure of state 1, and H3 is the enthalpy of the fluid in the liquid state at the pressure of state 3. This was all for the ideal cycle. For a real refrigeration cycle, there are irreversibilities caused by fluid friction and heat transfer, mainly from the fluid passing through the various piping connections. It is also hard to precisely control the phase of the fluid at each state. Usually the fluid is slightly superheated, entering the compressor, as opposed to being exactly a saturated vapor. The compressor and evaporator are generally not that close to each other, leading to a significant amount of friction and heat loss in these pipes. This means there must be an increased amount of work in to make up for these losses. And finally, the compression process will never be isentropic in real life due to some inevitable friction and heat transfer. This could either increase or decrease the entropy overall, so we don't really know where to put 2' on the TS diagram, such as the one seen here for real refrigeration cycles, and compared to the ideal cycle we have been evaluating. We have mainly analyzed the refrigeration cycle so far in this video. However, as mentioned a couple times, a heat pump is exactly the same as this, but just has a different objective, heating a hot space as opposed to cooling a cold space. Heat pumps are usually used with atmospheric air as a working fluid, except in humid climates where frosting makes this less than ideal, or with well water. This leads to higher COP values, but are more complex and require a water source. One huge advantage of a heat pump is that it can be generated by adding a reversing valve to an air conditioning unit. In other words, an AC unit can be transformed into a heat pump and vice versa. An AC unit is essentially a refrigerator using air as a working fluid. And remember that a heat pump is just a refrigerator in reverse. In this case, the condenser of the heat pump, which is inside the house, functions as the evaporator of the AC unit in the summer, and the evaporator of the heat pump, which is outside the house, serves as the condenser of the AC unit. These are most useful in climates that need a lot of cooling, but only a little heating. Here are diagrams of heat pumps on the left and AC units on the right. They are exactly the same, other than what is deemed the hot fluid and the cold fluid. The definition of each is compared to the outside temperature. And the direction of travel of these fluids, notice the change in the direction from the reversing valve. In this video, we've analyzed the simplest type of refrigeration system. Of course, there are many more complicated ones as well. Some of the more common ones are cascade refrigeration. This makes use of staged cooling cycles and is useful if large temperature differences are present. Gas refrigeration systems. The version analyzed in this video was comprised of both gaseous and liquid phases. There are refrigeration cycles that use only gaseous working fluids. These are basically the Brayton cycle in reverse. And absorption refrigeration systems. In these, the refrigerant is generally a solid, which is absorbed into a transporting fluid. If you want more information on these, they're in Chapter 11 of the textbook. Those are the basics of refrigeration cycles. Here is your pre-lecture example for this video, as well as the answer. I'll be happy to answer any questions you have about the material in this video during class later. See you then.